Okay. Thanks everyone for coming. So it's my pleasure to have Adil come and visit us. He's a professor in USC, and he's also a research scientist at Google. And he works on a bunch of things we all know about, like machine learning, high dimensional statistics, and now in Google, data and data related problems for LLMs. So,
Well, it's really specific.
yeah, but he's that
He
specific.
works on data and data specific problems.
LLMs.
Oh,
Okay, great. Thank you so much for the invitation and also for the introduction. It's a great pleasure to be here. And today I'm going to present the work that I've been doing in the past year or so. It's in collaboration with many great friends and collaborators. Some of them are at Google Research, notably Sujay, Indrajit, and Rudrajit were affiliated with UT. Rudrajit was a former PhD student that he's now at Google Research. Okay, so the talk that I'm going to present is based on the following intriguing observation. Suppose that you have a model that's trained on noisy data. You use the model to make prediction on the same data set. And again, you retrain the model on its own prediction. And it has been observed that it's going to improve the performance in general setting and under different problems. And this is very interesting. When I encountered this one, it looks very suspicious because it seems that you are learning from nothing. You're just retraining yourself on the same thing. But it's been shown empirically that it's been very successful. And there has been some also theoretical follow-up work to say why this is happening. So what I'm going to do is that I'm going to give a brief background on the work that has been done on this intuition in different topics and self-training and distillation. And then once we are done with the background, I'm going to focus on what we are doing. Okay? So one area that has been focused on this intuition is called the self-training. And the setting is that you have a semi-supervised learning problem. You have a data, part of the data that has the labels, part of the data that's unlabeled, and you want to train a model on that. So the most naive, stupid things to do is to throw away the unlabeled data and just train the model on the labeled part. Okay, but if I want to use the entire data set, both the labeled and unlabeled data, the idea is that I'm going to train the model on the labeled data and then use this model to predict the labels or responses on the unlabeled part of the data, and then treat these predictions as like the target value, and then refit the model to the entire thing. Okay, so that's the general idea of self-training. If I want to be more concrete, let's say I'm putting D for labeled data, D tilde for the unlabeled data set. I train the model by minimizing some, let's say, empirical loss. And this is the iterative approach that I'm going to do. Every time I have a current model based on part of the data that I have, I use the current model f of t to come up with some pseudo labels on each sample xi. So this phi is some pseudo label function. Maybe it's just hard thresholding, or maybe it's something fancy. And then in the next update, I'm going to use the actual labels on D and the predicted labels by the current model on D tilde. And as the model is getting updated, these y tilde, these predictions also get updated. So I get progressively different models. Okay? You can do it even in slightly more complicated way, where at each iteration, I'm going to use only part of the D tilde, not the entire D tilde. So it could be, for instance, based on the confidence score. I only use the data in D tilde that the current model is confident about its prediction. For instance, the largest of the model is large enough. Okay, and then you try to progressively use different parts of the data and do it in a cautious way. So that was the self-training in the literature. The other one is the knowledge distillation by this very celebrated paper. And the core idea of knowledge distillation is that I have a teacher model. It has a high capacity. I'm going to train this teacher on the data. And then I want to have a smaller, lower capacity student model. I want to do some compression. I don't want to deal with billions of parameters. So the question is, how can I depart some of the knowledge that this teacher model already have to the student? So the idea is that the student would get the training data, will see the predictions from the teacher model, and also the hard labels, the actual labels on the data, and wants to mix them, combine them in a way to be as good or sometimes even better than the teacher model. Okay? And a very natural way to combine these things is to think about the linear combination, a weighted combination of the labels that you get from teacher and the actual labels from data. Okay, so that would be a linear combination. And
Question.
yeah,
I'm sorry. In the other or over-parameterized regime, and do you have to make sure that you don't get into the under-parameterized regime if you start in the over-parameterized?
okay, this is a very good question. So it's mostly an over-parameterized, but there is an interesting work by Sujay and Rudraji did. I'm going to get to that one based on the variance trade-off. Sometimes you need to make this even larger than one. So depending on what regime you have, you may want to even anti-learn the actual data. So depending on which regime you are, it could be very interesting. Any other question? Okay, so the idea here is that this teacher model has higher capacity and can better learn the distribution of the labels, and somehow this knowledge is compressed and given to the lower capacity student model. There is also a reverse direction, weak to strong generalization that some of you might know. It's the other way, that you have some weaker model and now you want to come up with a model that's better than that. So that would be the reverse direction. Okay. Now, what's the self-distillation? Self-distillation is a specific case of knowledge distillation where teacher and students are the same model. Okay. And this is surprising because what it's doing is that you train a model on the data. Let's say this is x0, y0. The first model you get is f0. This model is going to make some prediction y1 on the same data. And then you do the retraining based on the predicted y1. And you keep doing that. So why I say it's surprising? Because it's the same network structure. It's the same training algorithm. It's the same data. Everything is the same. There's no new information, but still the model gets improved. So that's quite interesting. And this is with the self-distillation. And people have been trying to understand what's happening theoretically. Empirically, it's been observed that it's useful. So you start from x0, y0. So let's say y0 is a noisy label. You train a model, it's called f0. And this model is going to make predictions on the same data, x0. So this y1 would be the prediction.
Are they hard to solve?
We'll get to that one. Okay. So either you need some regularization or these are hard labels. If I don't do anything, it's not going to improve because you just predict and then you fit the same model. So there is some nonlinearity happening.
Very similar to the first slide that you had, right? The self-training process is kind of like that. You train and then you.
So in the self-training, so when they talk about the self-training, it's more on like semi-supervised, that part of the data has labels, part of the data doesn't have. Here, everything has labels. So it's even simpler, but more.
So here there is no new data.
No new data. There's no new data.
So when you say it's better, do you mean compared to if you trained on the hard labels or better compared to without?
Better compared to the F0. So you could.
You could also maybe improve things by just training, like doing another pass, right? Through the same data.
No. So I'm not doing like, so let's say you have some loss and you minimize it to global optimum. So it's not about like SGD or how many runs of data that you have. Okay, so the training is, the loss function is the same. Let's say you minimize to the global optimum, you get the model. And just by retraining using the same data, same model, same architecture, you're gonna improve. Yeah. Any other question? Okay. So one theoretical work was by Hossein Mobahi and Peter Bartlett that they consider a setting that you are fitting nonlinear model from a predefined Hilbert space to approximate the model to your data with L2 regularization. And what's shown is that this idea of self-distillation, what they do is essentially adaptively changing the regularization here. So it has some sharpening effect. As you do the retraining, you're going to narrow down the class of basis function that it's going to be used to approximate the model. And so the idea of self-retraining is you start from like a large class and somehow sharpen the model to go through the right basis function.
Decrease the regularization.
So you decrease, and this tells you that if you do a few rounds of self-distillation, it's going to improve the model performance because it's reducing the overfitting. But if you do it more, it's going to hurt the model because you go to the underfitting. So there is some sweet spot for the amount of retraining that you need to do.
This is an RKHS,
This is RKH.
so it's linear.
It's linear. It's the actual model that they did coming, they are assuming it's nonlinear, but they fit linear.
Oh, it's linear.
The model is linear, the data is not linear. Yeah.
I'm a little confused. If you're training to the global optima, then it doesn't matter where you're starting initialization doesn't matter, right? I don't understand why the first level, if each time.
Why there should be any improvement if you're saying why there should be any improvement if you just fit your prediction again and again.
Because we throw away all the weights and just something random, we're going to the global optima.
So there is a cache. So once I get to the model, you see that there is some nonlinearity, like hard thresholding or regularization that is in the picture and answer those questions. So if there is nothing, if I just predict something and then I refit that, it should be the same model, right? Because that was the global. I agree.
You say that the model improves generalization performance of this.
Yeah, that's fair.
You think even then, so if you take some data set and train to the global optima, now I start from some different initialization, but train to the global optima. What time is the
You're changing your loss. You're
different time?
The Y's are different.
You have to take.
Yeah,
Your predictor, yes, but that's in different velocity.
yeah, but the loss has changed. Right?
Even global optima is doing this.
Not the same loss.
If you push the like filter regression, then it's not room for itself.
Yeah. Yeah.
Yes, we can have these loss and. Yeah.
So you train F1, I just use the labels from F0 or I use the mixture of F0 and real labels?
All good questions. We'll get to that. Okay, just bear with me a few minutes. Okay, and the other work that I wanted to highlight by Rudrajita and Sujay was again understanding this idea in linear regression and through the lens of the bias variance trade-off. And the interesting observation is that, as I said, sometimes the optimal weight here is larger than one, which means that you want to anti-learn the actual data given to you and put more weight on the predictions coming from the teacher model. And so that was very interesting. And what's the framework? I'm going to call it model retraining because it's not exactly either of the previous framework that we have. It's close to the self-distillation, but it's not exactly the same. And the idea is that I'm going to iteratively fit the model, f of t, by minimizing empirical loss. But it's more about like how to come up with like pseudo labels at every iteration. So I'm not taking a linear combination of the losses. It's more about how to combine, how to mix the initial noisy label y hat and the current predictions from the model. Okay. And this g of t, I'm going to call it some aggregator function. And the question is, what's the right or what are the natural way of combining these things together? Okay. But everything, all the mixings are happening in coming up with the new label. Okay. Some of the questions that theoretically is interesting is, can I come up with the condition that retraining always is going to help the performance under those conditions? Or is it always useful? Are there cases that retraining is not good? The other thing is, if I do it like multiple iteration, does the gain keep going up or does it saturate at some point? So what happens if I do it multiple runs of retraining? And the other question is, if I give you specific data generative model, can you tell me what's the optimal aggregator function here? So these are the questions that I want to get into. So the talk has mainly two parts. There's a third part that I hope that I get like spend 5 minutes on that one, but it's mostly two parts. The first part is if you do retraining with predicted hard labels. Okay. And I think it would clarify some of the questions that Sanjay had. Okay, so let's focus on two specific type of aggregator function, or let's say scheme of retraining. One is called the full retraining, and the other one is consensus-based retraining. So full retraining is every round I make predictions on the from the model on the entire data set, and then I just hard threshold. So the only round that I'm going to use the actual given label is the first round. After the first round, I'm not going to use y hat anymore. Okay? It will be only the hard threshold version of my own prediction. So in this case, the aggregator function, if t is bigger than 1, is just sine of y, just hard threshold. And y is the prediction that you get from the current model. Okay. The consensus base is saying that I don't want to use the entire data set when I'm retraining. I only focus on part of the data that the current model is confident. So if y and y hat have the same sign, which means the given label and my predictions agree in terms of the sign, I'm going to use y hat, the original label that's given to me. Or you can take the sign of y, doesn't matter. It's the same, right? So I only work with the parts of the data that I'm more confident and do the retraining on those parts. Okay, so this is called the consensus-based retraining. Okay, a quick illustration before we get into details. This is binary classification. I'm using different colors for different classes. And circle means that it's the correct label. Cross means it's the incorrect label. Okay. So in both of them, you see that there is some mistakes in each class. Here, if I do the retraining, you see that most of the mistakes are gone. But here, you see that there are still lots of error here. And the difference between these two illustrations is that here you have a large separation between the classes. So it's saying that if the two classes are separate enough, probably the effect of self-retraining is going to be more significant. But if the margin is small, then using the same setting with the same sample size, the same feature dimension, everything, the effect of retraining is not as good as.
What's the model in the box here?
The model here is Gaussian mixture model. So I'm going to get that. That's the first model that I'm going to analyze. So it's the Gaussian mixture model, and then I'm going to tell you what's the estimator, the linear estimator. Okay. Back to Eric's question. So this is the Gaussian mixture model. You have the labels plus minus one, and mu is like the separator, the mean of the classes, and you have like a correlated Gaussian noise. Here, the norm of the mu would be like the degree of separation. So the larger mu means that the classes are separated enough. I generate n samples from this data. The data points are in d dimension. And once I have the labels, I'm going to flip each of them randomly with probability p, okay, to add some noise to the initial data. Okay. What's the model that I'm going to use to fit to this data? It's something very, very simple. It's a linear estimator. It's y hat xi, sum of those. Okay. So the other way that I can think about that is I'm going to look at the class of positive labels, take the average of the features there, look at the negative class, take the average of the features there, and then I take the difference, but I need to normalize with the frequency of each class. So this would be like a very simple estimate of mu, the separator. Okay. Now, the first model that I have is theta at 0. I use the theta at 0 to come up with the labels and hard threshold. So that would be my predicted labels. And then I'm going to refit the model using the same class, the same linear estimator. The only difference, I'm going to use y tilde here instead of y. And now the question is it a good idea or not? What should be the impact of p and margin of the classes, feature dimension, what should be the relation between them? So I see some improvement. Okay. The setting is clear. Okay. So the first result that we have, and I've been trying to be informal, but at the same time to be correct, which is hard. So if you want to see the exact form, I think it's better to check the paper. But here I'm just highlighting the terms that I need to give the intuition. So the way that we want to see whether the retraining is going to improve is we have a lower bound on the test error of the initial model and an upper bound of the test error of the retrained model. So if I show this upper bound is lower than this lower bound, it means that I have some improvement. Okay. And if you look at these two bounds, it's mostly the same. You have n over d here and this gamma over 4. Lambda means the minimum eigenvalue of the covariance of the noise in the data. But the difference that you observe is here you have 1 minus 2p squared. Here you have 1 minus 2p. Okay. And this gives us some hint that maybe depending on what's p and connection to n and d and gamma, you can make this one to be lower than this one because when you square, it's going to be smaller, but you have a negative. So you could be in the setting that this becomes bigger than this. Okay. And you do some
What was gamma again?
gamma is the margin of the class.
Margin?
Yeah.
So separation.
Separation. Right. So if you just massage this one and try to get different corollaries from that, one corollary that you get is you have some improvement if you do the retraining if this condition holds, and this is only sufficient condition. I wouldn't take the upper bound serious because I think it's an artifact of the analysis. And anyway, if n is bigger than d squared, it's not really interesting. We are using way more sample than the number of dimension squared. So focusing on the lower bound, one thing that we observed is if gamma is larger, if the class becomes separate more and more, you can see the effect of retraining at smaller sample size. But if gamma is small, you need to have larger sample size so that this effect kicks in. Okay. The other thing that you can observe here, quantitatively, it's not just about this guy become bigger than this one, so become smaller than this one. But if I want to see how much gain you get, it depends on P. And you can see that if P is growing to half, so you are getting like very noisy, then the improvement of retraining becomes more significant. Or in other way, if the initial model is very noisy, self-retraining is very good. But if P is small, the initial model is already good, then self-retraining gain is not that much if you fix N and D. Okay, sounds good? Any question? A quick note about the proof challenge here. Everything is simple. So when I was thinking about this problem, I was like, this is easy, some concentration and everything should work. So it's true for theta at 0. We can analyze the tessor of theta at 0 quite simple, but theta at 1 is a bit tricky because this y tilde depends on theta at 0. And theta at 0 is based on the entire data set. So the label that I get for each sample depends on all samples in the data set. It's not just on I. Okay. And because of this correlation, this becomes a little bit hard to analyze theta at 1. You need to do like one of these leave one out technique to deal with this correlation here. It's a bit more complicated. Okay. Now, what was the main motivation that we started working on this self-retraining? Was because of the differential privacy. How many of you know differential privacy? I've heard. Okay, quick 1 minute description of differential privacy is that I want to give some deniable plausibility for the records in the data set, in the sense that if I give specific response and say this is your response, you can say maybe it's not my response, it's because of some randomization or noise that you added into the data. So what's the definition, the formal definition of differential privacy? If I have two data sets, D and D prime, that only differ in one unit. So this is like the unit that you care about is privacy. And you have a randomized mechanism that they call it A. If I apply A on D and D prime, I want the output distribution to not change too much if I have just one single replacement in the D. Okay? So the outcomes of the mechanism are sort of insensitive to one record replacement. And this epsilon here tells you how much it's going to change. So this is more like a privacy loss. Higher epsilon means that you have less privacy. Okay. Now, what's the label differential privacy? The label differential privacy is when I only care about the privacy of the labels. So let's say this you have some survey and then people are responding to the survey. You have some public covariates for the users. So I don't really care about the privacy of XIs, but the response, how they're going to respond to the question, that's some sensitive information. So I want to make sure that this is made private. Okay. Now, the general idea of differential privacy is that you need to do some randomization. Either you need to add noise, or maybe I flip some of the responses. So a very classical way of doing this is with some probability, I'm going to keep the responses as it is. With 1 minus that probability, I'm going to randomly shuffle it with another response. Okay. So if I tell you your response was, I don't know, this, you can say, maybe this was my correct response, maybe it's the shuffled one. So it gives you some way to get away from committing to this response. Okay. But if you do the randomization, if you add noise to the label, obviously it's going to degrade the performance of the model. Now, the interesting things about the differential privacy is something called post-processing property, which means that if something is differential private, then you start to run other algorithms on that. You post-process that. It doesn't increase the privacy loss. So it's kind of, if it's epsilon dp, it remains epsilon dp. So here the idea is that if something is already randomized to be private, how can I improve the model performance by running something post-processing on that one? It doesn't increase the privacy loss, but maybe the trade-off between model utility and privacy loss is improved. Okay, so that was the main motivation that started to do the retraining. Okay, and a couple experiments to show if it works. So here I'm doing a ResNet with 18 layers on CFAR10. And these are the values of epsilon 1, 2, 3. So again, epsilon is the privacy loss. So smaller epsilon means that you are more private. So your test accuracy would be lower. But as I increase the epsilon, you have some non-privacy or some leakage, so you can hope for getting better models. So the accuracy is going to go up. And you see that if you do the full retraining, you already have some improvement. But if you do the consensus-based, the improvement will be higher. So it's saying that the consensus-based maybe, at least for this setting, is working much better. And for the consensus-based, the intuition is that you are retraining on a smaller subset of the data, but this is the part that you are more confident. Okay? So one thing that you can check is to see what's the average accuracy of the predicted labels on the set that you choose for retraining. So here, the average accuracy for retraining set would be much higher than if you do the full data set, but the size of this data would be much smaller. Okay, so the size of data would be 30, 55, 76%.
So in the consensus-based retraining, how do you find the final predictor? So you get a different subset of signals, even a predictor, but then like is that getting majority vote of that and like what it will.
No, it's so you come up with some model on the entire data. So that's the first thing. And then you check what's the prediction of this model and the initial given label. If they agree, it gives you a subset. And then you do the retraining only on that subset. So it updates the model, but the model can give predictions for everything, right? It's just okay. So so we will get to that one. So here you throw away and you just it's a linear estimator in theory, so you can just refit that. But in like more complicated setting like this one, you start the gradient descent from the initial model. Like if you have f of t, ft plus 1 is obtained by running the gradient starting from f of t. Any other?
So labels are soft labels or
Hard labels. So even if you come up with the predictions of the model, you're going to turn them into hard labels, and then you do the retraining. If I don't do that, then it's not going to move the model, right?
okay.
If it's, I think that was what Sanjay was saying. If I make the prediction of the model and I get to the global optimum, and then refit the same thing, it's going to give the same model. But the catch is that you're going to do the hard threshold. Because of this nonlinearity, then it's going to update the model. Okay. And again, another experiment, it's the same model, ResNet, C400. Yeah.
When you do the hard thresholding, then you're changing the distribution of the data. I mean, you're changing the data distribution, changing the new data distribution. That's all. How does it work?
Data distribution, you mean the label, right?
So I can just throw everything away. Just changing the joint between the teacher and the label.
Mm-hmm. Yeah.
And so by doing that, isn't there fundamentally a bias? You're moved up. Suppose you got infinite data and you're doing population in the first one. And then when you do it with the new one, you are training for some other distribution. So why shouldn't it generalize better?
Yeah, I agree that it could have some bias, and this overfitting, underfitting comes into picture. So that's the main reason of all of this theory. So we'll get to that one. And then at the end of the talk, I'm going to connect it to best of n. And the question is whether it's like overfitting or why it's working.
I think it's not just that you don't have infinite samples in the first round. The sample, the labels, that's the original labels.
So I see the assumption is the original data is not the true data.
Yeah, no, it's not true.
Why your that
You can think about it as a way of denoising. But this overfitting, underfitting, we'll get to that. There was Okay, so this was again ResNet on C400, and again, you see the improvement. And this is for when I talk about the baseline, this is randomized response framework, but it's a fancier way of doing that by the many others. But they use like a prior distribution of the labels to do the randomization. So that's what they use for the baseline. Yeah. The other experiment, if you do BERT on like AG news subsets, again, you see that consensus-based is working better than full retraining. Okay. But we don't have the analysis for consensus-based. So that's an open theoretical line if someone is interested. Yeah.
How is that different from boosting? Like boosting also like you have more picture errors. And then you want to errors, you try to relate the sample. And then you train on the related sample. But they're trying to target like the cases where I make more mistakes. But here it's also like you find your errors where there's mismatch. You kind of 0, 1. And boosting is like exponential. Exactly. Yeah. Because you're getting to be more. But it's integrating. Yeah, correct. It's the exact. So it's anti-boosting. It's anti. But it's not boosting because you're not going to the original marks. It's in your ensemble model. If you get a boosting just well, then it's like but boosting is highly normalized. So that boosting is extremely normal. You do boosting with noisy energy. That's a very normal. Right, so this is all the bus.
Okay, thank you. Okay, so let's go to the second part. It has the boosting in it. That's why I was not arguing against that. Okay, so a quick recap on what we've been discussing so far is we had two specific choices of the aggregator functions, full retraining, consensus based. But we were also doing one round of retraining. So the two directions that I want to generalize is what about the other aggregator functions? And what if I want to do multiple rounds of retraining? Okay, not just one round. Yeah. And as I said, even the one round has some complication because of the correlation that you get on the predicted labels on all other samples. So the way that I'm going to do is I will use the machinery of approximate message passing, the AMP, and it's going to slightly tweak the retraining algorithm, and it gives us some good way of analyzing things and understand what happens to the retraining. So there will be some correction to the retraining algorithm. But before doing that, let's think about the full retraining. I can write it this way. Y hat is the noisy label. The initial estimator that I had was X transpose Y hat. And here the scaling doesn't matter. Only the direction is important. So I'm going to scale it with 1 over root n. It's going to be more convenient for the analysis. And then Y1 would be my soft predictions on the same data. I'm going to take the sign. So that would be the hard labels. And the X transpose sign would be the retrain model that I have. Okay. Now, in general, if I want to work with like a aggregator function g of t, every time that I'm using this guy here, instead of working with sign of my prediction, I can work with g of t of the current prediction that they have and the initial noisy label. So I can bring back the initial noisy labels at every iteration, not just the first one. And then think about how to mix them with the predictions with of the current model at time t. Okay, so I have some g of t here. And once I have this model, the soft prediction would be x times. Okay, but this is just rewriting thing, but using a general aggregator functions. And if I think about the full retraining and consensus space, these are given by these two choices, sign up this guy or having this agreement between yt and y. Okay. Now, what's the modification that I'm going to do? At every iteration, I have some correction term added here. The role of this correction term is essentially to kill the dependency that we had between these estimates across T up to first order. So I'm talking very vague, but this is like the general idea of what's happening here. Okay. And these are coming from this machinery of AMP, approximate message passing, that's trying to approximate message passing, belief propagation on dense graphs. And it also has connection to statistical physics. So these terms are called on-cyber terms in that part. You have some specific formulation, like CFT here depends on the average gradient of your aggregator with respect to the first one. So there is some specific formula on what CFT here. Yeah. Now, if you want to see what's the role of this correction in terms of the analysis, what happens is that if you want to analyze this iterative procedure, it's the same as removing this correction term, but resampling the data at each iteration. If I refresh the data, then there is no correlation among these estimates. Okay? But of course, you cannot do that because this X is given and fixed. But I want to play the impact of this refreshing the data at every run. We're adding this correction and playing the same role up to first order. Okay? So that's the role of this correction. But one other interesting thing that comes with the AMP is that if you think about these estimates, theta t, these are like high-dimensional objects, random objects. They are random because they depend on the X, and X is random data. Okay? So I need to work with like large random object. But the interesting thing is that you can come up with deterministic equation that tells you exactly what happens on the trajectory of these objects. So what do I mean by that? You can come up with something called the state evolution. So these are like some deterministic updates in terms of like a couple variables. In this setting, we have two variables. So this is something that you can run even before running the algorithm. Okay, so this gives you like a deterministic equation. And then once you have these quantities essentially would capture the behavior of these high-dimensional random objects. So in other sense, although you are in high dimension, specific concentration kicks in. So for every fixed iteration, I can tell you what would be the behavior of these estimates if n and d goes to infinity. Okay? So I'm very sloppy, I'm very hand-wavy describing what's going on, but let's see how it's going to help us to understand the impact of self-improvement. So again, let's start with the Gaussian mixture model. And I'm in the regime that d and n, both of them are going to infinity, but the ratio is going to some constant. And this constant could be anything, less than 1, bigger than 1. It's just saying that the sample size and feature dimension are growing at the same rate. Now, when I say the state evolution is capturing the behavior of this object, it means that if I look at the empirical distribution of my estimate at each iteration t, I can tell you this distribution is converging to something. It tells me exactly what's happening in terms of the estimator at every iteration. And once I have this result, I can see what would be the test error of the system. Okay. So one assumption that I didn't mention here is that for this, I'm assuming that this separator, the empirical distribution of the entries is converging to some random variable that they call it n. This is like the assumption. But once you have this one, you can prove this about the joint distribution of your estimator at iteration t and this one. So this estimator is supposed to estimate mean. Okay, so I want to see how this joint distribution behaves. So the marginal of this one is converging to m. This is the assumption that they have. But saying that my estimator would be a scaled version of what I want to estimate plus some Gaussian noise. But every iteration, the estimator is behaving like this. And so this is like the final message of this. Now, once I have this about theta at t, you can easily compute the test error of that one under Gaussian mixture model, and it's given by this. Now, if I tell you what MT and sigma t is, and that's the role of a state evolution, these are like simple recursion that you can compute, it tells me what's the performance of the state at t and what's the impact of retraining. Okay, sounds good? The overall description is here.
So I guess the genes, are there in assumptions of what type of function?
Yes, pseudo-Lipschitz. But even if it's not pseudo-Lipschitz, like the consensus space, what you need to do is to do some smoothing. And then it becomes important what's the order of taking the limit. Like you can smooth with some parameter beta, you do the AMP analysis and then take the beta to or go to infinity to make it like a sharp turn. Okay. Now, if you think about this one, it's based on MT and sigma t. MT is like the strength of the signal that you want to estimate, and sigma t is how much noise you have. Okay. And you see that from this result, it really depends on the ratio of these two, on the SNR, signal to noise ratio. So I can try to write the test error in terms of eta of t, the SNR. And now the question is, what's the optimal choice of G of t? Let's say I have run this retraining for t iteration. In the next round, the question is, what's the optimal G? And I can change this function across iteration. I don't have to stay with one specific function. Okay. So the base optimal choice of G of t is the one that is going to minimize the error in the next round. Or another way is the one that maximizes the SNR. So I can try to see what's the optimal G of t that maximizes this eta of t. Okay. And I'm making it easier for you. Let's say you trust me, I computed the base optimal G of t, and it's going to take this expression under the Gaussian mixture model. So this is the right way to combine my predictions and the noisy label. The function is always between 0 and 1, which is convenient. I always treat this G of t as like a pseudo label. It depends on the class frequency pi minus and pi plus. It depends on the SNR at the current iteration. It depends on alpha, which was b over n, and also the split probability. Okay. You can also try to write this guy as e to the log of this and combine them together, and you get something like a logistic form where you are combining y and y hat, but with different weights. Okay. Y hat was the initial noisy label, y is my current prediction. And you see that here, y hat is weighed by the flip error probability. Here, it's weighed by the SNR. So intuitively, it's saying that you start from y hat, it's the noisy source of data. And as you are running this retraining thing, you also get another source of information about the labels. Both of them are noisy. And the question is, how should I combine them? It depends on how much you can rely on each of them. So you can rely on y hat depending on what p is. You can rely on y depending on the SNR. Okay, so if SNR is very large, I want to weigh this guy more. P is large, p is small, I want to weigh this guy more. Yeah. So that would be the optimal G of t. Yeah.
If the SNR, so if I have a noisy data set, is the SNR something that can be estimated from the data set, or does it have to be given?
Very good question. It can be estimated from the data set. So this is what I'm going to discuss. A couple experiments on how it works. So the dots here are the experiment. The curves are the theoretical curve. And you see that with n and e are a couple hundred, you already have a good match. So state evolution is actually working and giving you the right behavior of the model. It really matters on which aggregator function you're working with. So if you go with the optimal one, you get this one. If you go with the consensus space, you get this. Full retraining, you get it. In another setting, you could see that the full retraining is working worse, and even it's going up. So retraining is not good for full retraining, but it's good for like consensus or output. So the role of aggregator function is very important. Okay, another intuition that what?
What is the setting? What is the experimental setting? Is it linear?
It's a Gaussian mixture, the same thing, the same as
Is it a linear model?
it's a linear. It's whatever you get from AMP, it's a linear. Yes.
So the biggest is when you have the optimal G, put that in. What do you know about the optimal error? Is that a dependent function of the
Very good question. This slide, next slide. Okay. So I talked about the state evolution, but think about it as like some function f. But there is some specific form that I'm not writing here. And I said I can write everything in terms of the SNR. So this is the way that the SNR is updated. So let's say this function f, I plot it here. This is the black one. And then I want to see what happens as I'm running this retrain. So I can think about it in terms of the cobweb plot, right? So I take the line now y equal x. Now, if I start from the initial model here and do this retraining, the state evolution is telling me what happens to the SNR. And the higher SNR means I'm going to get better model. So in the next round, you get here, then you get here, you get here until you converge to the fixed point. Okay. But it also tells me an interesting thing, because if I start from a model that's not good enough, so SNR is small, the SNR is small, retraining is going to improve the performance, converge and get saturated. But if you start from something that's already good enough and you do the retraining, it's going to hurt the performance. So the quality of the initial model is very important. And here for Gaussian mixture, you have a clean separation. It can tell you exactly what regime you are in. Okay. But again, once you have this one, it tells you what happens with SNR, and so you can see what the gain is. Okay. It gets saturated eventually. It's not that you always get improved. And you can make it formal once you have all of the functions and everything. So that would be the result that we get. If the margin is bigger than some specific value, and the initial model is not good enough. So P is at least P star, and it's at most half. So if it's noisy enough, then you see that it's going to consistently improve, retrain. Otherwise, it's going to degrade the performance. And this P star is given by the fixed point. So there is some way to see what's the right amount of noise for this model. Yes?
So whatever this model is, to which it converges at the end, whatever the model is, like at the end you get the saturation model.
Mhm.
Like, can you say something about that as like just one-shot learning? Like what are we learning? Shot. Rather than like retraining multiple times.
So you want to achieve this model with one shot.
Shot. Yeah, just want to know what model class is that solution.
Good question. I don't know.
Yeah.
Yeah,
You know, model class?
I'm not sure if there's a way to get here by like one step, but that would be very interesting.
Related to that question, so let's say you start training with set x1, and then you retrain by adding set x2.
Mhm.
Now, how does that compare with training with the union of the sets x1 and x2?
So this one would be, you can handle that because you can choose different G, right? Like if I want to do like this consensus, for example.
Yeah,
Yeah.
is the retrained model, does it compare, how does it compare with the just one-shot training with the joint set?
I'm not sure if I get the question.
I mean, you could, instead of using x1,
Mhm.
you could use the union of x1, x2.
And what are X1 and X2?
The original training set plus the additional set that you use for retraining.
So it's the same set.
It's the same set, but
It's
now
yeah, it's the same set. I'm using a different label. So X1 is,
you assume that x1 also is labeled, but in with the retraining,
Yeah.
you just don't use the labels.
oh, so you are using X and Y and then X and Y tilde,
Yeah,
and then retrain on the inheritance.
how does that compare to the retrain?
But that one, at least for the linear regression, I think it's more like taking a weighted sum of the losses instead of combining. So it's a different way of retraining, but I don't know how it compares. But I can write it as the one that Sujay has, the linear combination of the loss on X and linear combination of and the loss on
It probably worse. Because you're adding back the noise.
I think it's the one that you look at. Do you think the limiting trade network corresponds to the one just includes everything? Neutral.
We'll take it off. There's also been one early question. So you said that when you have something like the constant retrieval is like input new data like X. But if I don't have that, do you know that it's going to be always worse? Like, is it always better to have new fresh X?
You mean, is it always good to have this X tilde?
So
These correction?
And so I didn't pick up correlation because of having the same X at every step, right?
Mhm.
So I guess it's not clear to me that like, is that a good thing to have the same X or you should, I mean, suppose I give you new X.
So you are saying if I run the AMP but without the correction,
Yeah.
so it's going to be worse, and then also it has three parts.
So that, let's say
So, I mean, having the analysis easier is a separate.
Yeah,
question.
no, I'm saying that it's both. It's the analysis would be easier and also the performance is not as good.
So if I get a first step, actually.
Yeah, so there are like several work, not on retraining, that shows the AMP is like the optimal first order for this class of function. And that's because of the correction. If you don't have the correction, it's not optimal. So I'm guessing that it should carry over here, but I don't have specific results. I mean, experiment, I have removed the correction to see if it works better or worse, and it was worse, but not theoretical. Okay, any question?
So in practice, you won't have that. Right? The on-site account will depend on population quantities you don't know. So you can implement the algorithm. Right?
On the population,
Like the way you have presented this algorithm, you can implement it in practice.
why?
Because the on-site account will depend on some population quantities, right?
No, it's only a function of G, let's say. The derivative of the function with respect to this, whatever G you have.
Also, you can actually implement this.
Yeah.
In practice.
Yes. That's the point.
No, I mean, this is fair analysis.
Yeah, no, you can implement.
We have only a few more.
Okay, so I'm gonna, okay. So, this one, I'm gonna be quick. You can do the same thing, not only for Gaussian mixture, you can also work with the GLM, generalized linear model. So here, the probability of Y being 1 is some link function applied to X transpose beta. And again, the same thing goes through. You can come up with AMP algorithm for this class as well. It looks very similar. The main difference is that now I'm trying to estimate beta instead of mu. So beta is the parameter that I'm gonna estimate. And these insights carry over to this setting. So it's not specific to Gaussian mixture model. Again, you see that if the initial model is not good enough, self-retraining is useful, otherwise it's gonna hurt. Okay. Now, this is all good. We have the optimal aggregator under the GMM and GLM, but the question is, what if I'm working with some other data setting that I don't know how the data is generated? If I want to come up with something that's based on the insight that I have from AMP, but I can use it for other like complicated settings. And so we're gonna come up with something called Bayes mixed retraining. It's based on the insight that we get from the AMP. We don't have any proof because obviously we are not making any assumptions on the data model, but empirically, as I show you, it's gonna improve not only for the retraining, but also the consensus state. Okay. And the idea here is that the initial labels are given as a noisy source. So this is the way that they are generated. The predictions of the model at each iteration is also another noisy source of information for the actual label. And from the AMP, we were saying that if you have like a classification, binary classification, that this should be like a mixture of two Gaussian. And the mean and the standard deviations are given by this state evolution function explicitly. Okay. But you don't have to have the state evolution. I can try to estimate these in a data-driven way. If I come up with the soft prediction of the model at each iteration, I can try to fit a mixture of two Gaussian into this data. And there are off-the-shelf packages that tell you a good estimate of the variances, the mean, and also the frequency of these two classes. Okay, so you can try to estimate them in a data-driven way. And now the question is, I have two sources of noisy information. What's the right way to estimate Y from these two? So you can write the Bayes optimal estimator based on those. And the Bayes optimal estimator would be taking a similar form as what we had. Okay. Now, as I said, the quantities here, mu plus, mu minus, sigma plus, these are given by the package that try to fit a mixture of two Gaussian. How about P? What's the initial noise in the data? How do we estimate that? So we're gonna use the model itself to come up with a good estimate of P. So we only focus on the data points that the model is very confident, like the logit of the model is large. And then we treat the predictions of the model on those to be like the ground truth. And based on that, you can estimate the slip error probability. So this is the way that we approximate P to use this function in practice. Okay. Now, how does it work in like more general settings? So this first one is linear probing, and then I have uniform noise. So P is just one number depending on whether you are in the positive or negative class. And you see that here, like after 10 rounds of retraining, you are doing better than the other two. In the first round, it's not better than the consensus base. If you have like a different node, you can also handle this one. If like flipping from plus to minus is, I don't know, 0.45, but the other direction is 0.2. Again, you see that you get improvement using the basement retraining. So this was for linear probing, that I was preserving the body of ResNet 50 and just retrain the linear head on that. We can also do the full retraining. And you see that in this setting, these two, the performance is going down if you do the consensus base and full retraining, but with the base mix, it's going down. Okay? And this is the same thing with non-uniform. Okay, so it seems that in more complicated setting, it's also doing something that the consensus base and full retraining is not doing. Okay. Do I have 5 more minutes?
No.
No?
Yeah, we're running a little bit, a lot of questions.
Yeah, that was yes. Right. Okay, quick, and maybe
Yeah.
2 minutes. Okay. So we talked about the binary classification, and you can think about generalizing that to multi-class. Just instead of having a mixture of 2 Gaussian, that would be K Gaussian. But how about the self-improvement in language model? Okay. So the usual pipeline of training language models that you have a pre-training phase, you train a model on large amounts of data, and then you have some specific downstream task that you want to make sure that the model is capable of doing it. And usually you do either SFT or RL or a combination of those two on the high quality demonstration data that comes from the downstream. Okay? So focusing on SFT, what you can do is that I have a parameterized policy pi, and then I want to maximize the log likelihood on that SFT data that we have. So you start from some pre-trained data, and then you change it a little bit based on this loss function. So you run a few steps of gradient on that. Okay. Now the question is how to implement the idea of model retrain on SFT. Obtaining high quality data would be a challenge. So if you have like lower quality, can I improve the model? Okay. Now, if you think about the hard thresholding, what it does is you have the model, it comes up with like the soft predictions, and then you take the cipher. Okay. So if I want to generalize it, is I work with the logics for different responses, and then I choose the one that has the maximum likelihood. So this is like the hard threshold. Okay. So the idea that the very basic attempt would be to come up with the maximum likelihood response for each query, and then retrain based on those. So that would be the next round of the SFT model. Okay. So that is like what we are doing in hard threshold. But the challenge here is that this set of responses is infinite. When you have a classification problem, this Y could take 2 values or K values. So I can see which one has the highest threshold, highest logic, and go with that one. But here you have infinite number of responses. So how can I implement this one? Instead of trying to go with the best, the maximum likelihood, you can generate n samples from the current model that you have, and then choose the response that gives you the highest logic, and then retrain based on this best of. Okay, so this gives you a natural way going from retraining to best of n that people have been using to improve like O1. Okay. Now, instead of working with this logic as a way to implement this hard thresholding, so you can think about it as some internal reward, how confident the model is about its prediction, but maybe I have some other reward function. So when I'm doing this retraining and choosing what response I want to for the next round, I can go with argmax of my reward function, not just the internal logic that I have. Okay. Now there is some work that tries to connect the self-improvement with best of n. But this is more thinking about this approach as a sharpening mechanism, that you start from like pi of theta that gives you many possible responses for a query X. And every time that you do this self-improvement, it's more like I'm sharpening on some specific response. And this work is more about the connection between maximum likelihood optimization and sampling. So for some class of distribution, computing the optimization for maximum likelihood would be intractable, but sampling would be tractable, and the other way. So they use it as a way to understand the trade-off, computational trade-off between optimization and sampling. But not really in terms of like model improvement, as I was explaining. So the questions that are interesting is that the very first question that I think Sanjay also asked was, if you do this best of n, aren't you overfitting? Does it have any bias that you have? Or can we theoretically understand whether it's giving you any bias or not? Or even more, what's the right choice of n here? What parameters does it depend on? The other question, if I see the optimal n is 10, is it better to do one round of retraining and generate 10 samples? Or is it better to have like 2 rounds of retraining and generate 5 samples if I have some fixed computational budget? So these are some of the questions that I'm still working on. And then to understand what happens under what condition the best of n is improving, I don't think it's always going to help. What are the sufficient conditions, at least, that you can show best of n is the right thing to do? And also, best of n is just retraining on the best samples, but how about bringing back the noisy data that you were given at the beginning? What are the right way to combine them together? Yeah, so that was it. I'm going to skip the summary in interest of time. Thank you so much.